Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell below. You'll get notifications for this series and a bunch of others on our channel. We're doing multivariable calculus. Chapter 3 finally is vector calculus, and specifically 3.1 is going to be vector fields. This lecture, what we're going to do is vector fields on R2 and R3 on the plane and then in space. Of particular interest is gradient vector fields. Let's do that. First, as motivation, why do I want any of these things? Because I can finally start in this multivariable calculus and with some linear algebra and a few things that we have to now mash together and just call science and learning and understanding of the universe. We can put this all together and start understanding things like gravity and electric fields and fluid flow and all these kind of dynamics. For this idea, this is just a few of the examples in science where we're going to want the notion of what we're going to call a vector field mathematically. What intuitively that and where this comes up in a very visual form is when we look at airflow for wings and lift in airplanes and aircraft, or when we look at how to build dams or these types of things and we have narrowing channels and the forces that are going to act upon those. What we notice is as we get, for the water is a really good example to show, as what we're going to say at every point in the water flow, we're going to put a vector at that point in the water flow. And if the vector, if you're in the fairly wide channel, that means your fluid or the velocity is probably going to be what it represents. The velocity will be relatively slow, so the magnitude of that velocity will be fairly small, and so the vector will be smaller. As the channel narrows, the magnitude of the vector or the velocity is going to get larger and larger, so the vector in the channel are going to be much longer, or the magnitude of those are going to be much longer as the channel narrows. Let's give the specific mathematical definition of this scenario. Mathematical definition of a vector field is, first of all, we consider a subset D of the plane R2. A vector field on D is a vector valued function f, which assigns to every point x, y, and d not a number z like a function of two variables, but now it's a vector valued function of two variables, and it assigns a vector, capital F of x, y, to every point x, y. Our notation is now going to be, because it's a function of two variables and it's going from R2 to R2, what we're going to say is, and we're going to denote this function or this vector field as P of xyi plus Q of xyj, where I and j are the canonical basis vectors of the plane. Or what that says is, because he's 1, 0, you can use scalar multiplication and addition of these vectors to write it in vector form like this. In either case, this is the expression that we're going to use and the notation that we're going to use for vector fields over a plane. If, in particular, these are constants, then that vector field is going to be constant regardless and independent of the points, and we're going to call that a scalar field, which still defines a vector at every point, but the vector has the same magnitude and it's just going to be pointed in the same direction no matter what point you're at. Let's do a couple examples. All right, here's an example, and this is what a lot of textbooks do, so I'll do it the same way, and then you're like, well, how did you do that? So we'll narrow it down in the next example. I'll do one more before we go on further. Here's an example of what we're going to call, you don't have to know the names of all of these either, but this one's going to be, for obvious reasons, called a radial field. All we've done is, at each point, we're going to just create a vector which is the magnitude of the x and y coordinates respectively. What that's going to do is, if you are near the origin, you're going to be a vector pointing outwards, and it will have a relatively small magnitude, and as you move out from the origin, the magnitude of the vector will get larger. And this could describe any kinds of physical phenomena. The jokes are always going to start, so I can start them right now. We're going to talk about gravity. We can talk about this one too. Gravity sucks. It's going to go inwards. It's going to be an attractive force. And this one can be what they're talking about, dark energy. For some reason in the universe there's a repulsive force and everything is moving away this way, and this is what we're going to call a radial repulsive force field. This one is going to be a spin field, and you're going to have to start getting used to the terminology already. If I have a vector, which is unfortunate terminology, where we're going to call the vector xy, x is going to be xy. I know, I'm just going to follow the textbooks. Given that, the norm of that guy is exactly this, the square root of x squared plus y squared. So you're going to have to notice that what they've done is normalize this vector field, and that means that the magnitude of every vector will be 1 regardless. But then if you look at this, what's going to happen is it's going to spin Greek-wise or counterclockwise spin, and the magnitude of every vector will be 1 because we've normalized. The example I'm about to do, we're going to do this. Take it easy. and we'll look at the unnormalized one, but then the magnitude of the vectors will change as I go around also. Let's do that example, because you're asking yourself, well, how did you draw this picture and how do I do that? The definition tells you at every point, I draw a vector at that point. And in this case, the vectors are all going to have length 1. That's why I look at the same. At these points, I'm going to draw a vector. But as I move out, because x and y would get larger, the vector is going to get larger also. Let's do an example specifically of this one now. All right, so for our second example, we're going to tone this back a little bit. Basically, what I've done is not divided by the length of the magnitude of that vector. And we're just going to look at this. So I've sort of spoiled the surprise, but we're going to build it anyway so you can see how I do this. This, I'm hoping, is also a spin field, but not normalized. So the vectors will grow the further from the origin we get. Let's analyze. How do I actually draw the field? The definition of the vector field says at every point x, y, I'm going to define a vector at that point. And in this case, it's the coordinates negative x, y. To do that, I'm going to first look at what happens at this point, f of 1, 0. That is supposed to be, it interchanges the coordinates and adds a negative. That's 0, negative 0, 1, which is, that's not a point anymore. It's a vector now. And that negative 0 gives me who? J, turns out. And then let's look at this. Oh, so then we can draw it. Why wait? That says who is that vector? J is this vector. And therefore, I'm going to get that vector. Then what I'm going to do is f of this point, 0, 1, is going to give me negative 1, 0, which is scalar multiply, take the negative out. This is negative 1, 0, which is negative I. Who's negative I? This guy. So I'm going to get this vector. Also with magnitude 1, because I want the circle of radius 1. Well, just wait a second. F of negative 1, 0 is going to equal negative 0, negative 1, which is negative 0, 1, which is negative j. Who's negative j? This guy. Therefore, I get this vector with magnitude 1. And then you can see where I'm going with this, hopefully. F of 0, 1 is going to be what? Negative, negative 1, 0, which is going to be 1, 0, which is I. Who's I? I is this guy in space. So I'm going to get this vector. Coincidentally, what that shows us is, and we're going to prove it right away, but you can already sort of see it. It looks like we're on this circle of radius 1. And so the radius is 1. And the magnitude of f at these points happens to be 1. This is not a coincidence. Let's look at that. All right, so in general, I'm going to point out two things. The first thing I just noticed was it seems like the magnitude of the vector at the point was equal to the radius of the circle it's on. What? Yes. What is the magnitude of f? Nobody likes linear algebra, but that is defined as the magnitude of yx, this vector, which is the square root of the sum of the square of its coordinates. What? Which is the square root of the sum of the square of its coordinates, which is x squared plus y squared square root. What does that tell us? Well, what's the magnitude of x? The same thing. So the magnitude of f at that point is the magnitude of x viewed as a vector at that point. So what that says is the magnitude of this force field is equal to the length of the radius of the point x at every point. So as we go out, these circles, these vectors will grow as we move out to a larger circle. If we go to another larger circle, it will still do the same thing, but now the vectors will have grown in magnitude proportional to their coordinates or the length of the radius of their distance from the origin. In the one where we normalized, as you go out, all of the vectors are going to be the same size because we've normalized so they'll all have length 1 regardless of how far out we go. That will be the difference between the two spin fields. I know it's a lot at first, but the first thing I point out is the magnitude of this force field is equal to the magnitude of the original geometric vector, which is the radius that you're on. The second thing we have is the fact that it seems like from the picture also that it's perpendicular to the point that it's at. At 1, 0, 1, 0 is going this way. This is the vector, viewing it as a vector 1, 0. So if this is x, it seems like f was perpendicular to that at every point. How do we flesh that out? We use linear algebra again. If I look at f of x, y, dot product with x, the original vector, x is the vector x, y, then we're going to get that this is negative y, x, dot product with x, y, which is equal to negative yx plus xy, which is 0. We should hit a Pavlovian nerve from linear algebra. Watch some of our linear algebra videos for another playlist. That Pavlovian nerve is the fact that f is perpendicular to the point at which it's at every point. You know, I guess you don't need to know these things, but analyzing vector fields, especially ones that we're going to use in physics a lot, are extremely important. So the two main things are, at every point, the magnitude of this force field is equal to the radial distance from the origin. And the second thing is, at every point x, the vector field is perpendicular to that point. Let's do more. All right, now quickly, we've got vector fields on R3 is going to be the same thing. We're just going to have another coordinate. We're going to pick a region E now in R3. A vector field on R3 is defined as a vector function pi plus qj plus rk, where, again, I is the canonical vector 0, 1, 0, 0, j is the canonical vector 0, 1, 0, and k is the vector 0, 0, 1. So we can also, using scalar multiplication and addition of vectors, we can write this in this compact form. And when we're super lazy, we're going to get rid of x, y, z. We'll just say p, q, r as the coordinates. And then this is essentially what we're going to do. I'm going to draw it once. Drawing in 3 dimensions is harder. I won't make you do it either. I don't know about your other instructors, but if I make you draw vector fields on a regular, it's going to be in the plane, not in 3 space. It's hard enough as it is. But this is where we perceivably seem to be, is in 3 space. So let's look at some vector fields over R of particular interest. All right, of particular interest is Newton's law of gravitation. Yes, we've got a better version. Thank you, Albert Einstein. But for now, this works extremely good for things near Earth and in our solar system, etc. What does it say? If you have two masses in space, neglecting everything else temporarily, and you have a distance r between them, what Newton's law of gravity says is the magnitude of the force between these two objects is directly proportional to the masses and inversely proportional to the square of the distance between those two objects. What? This is why we don't like rhetoric. Algebraically, what that says is this would be the magnitude of my force, and what that says is we'll have a gravitational constant, which was found several hundred years later. It's going to be m1 times m2 times a gravitational or a proportionality constant, and it will be inversely proportional to, so 1 over the square of the distance. And then we're going to turn this guy into a slightly different version. What we're going to do now is phrase, we're going to put one of these guys at the origin in 3 space and say, what is the gravitational force acting upon the force field due to the mass m1 acting on m2? Let's do that. If we want to analyze that in 3 space, what we cleverly do is we move that picture. We put mass 1, or the object with mass 1 technically, at the origin. And then we want to say, what's the gravitational force of m1 acting on m2 as we get closer or farther away from that object? And what we notice is, first of all, if we call the position of the object at m2 as the vector x, which is x, y, z, we notice that that distance between them now is the norm or the magnitude of x. Therefore, the norm of x squared is r squared, our radial distance squared. And the force exerted on that object is radial inwards towards m1 or towards the origin, and a unit vector in that direction is negative x over its norm. This is how you always create a unit vector, divide by the length. So negative x would be going radially inwards, and then we divide by its length to get a unit vector. What does that give us? Putting that all together, what we see is the gravitational force acting on M2 at position X is given by that force field is the magnitude of the force, gravitational force, times a unit vector in the direction of that force, which cleverly happens to be, we know what the magnitude of that is by Newton's law of gravitation, m1 times m2 times the gravitational constant over the radius squared, times that unit vector, which was negative x over its length, which is also our radius. Putting that together, we get that that force field called the gravitational force field of object 1 is negative m1 m2 times the gravitational constant over the radius cubed times that vector x. And what that's going to say is everything is pointing inwards. Gravity sucks. Dark energy blows. The last thing we're going to do is gradient vector fields. A gradient vector field is just pointing out that we just didn't point this out the first time we defined gradients, but it is a vector valued function, and so that is exactly what we want. For a function of two variables, it is a scalar function. It creates a number, but from that scalar function, the gradient vector is this guy, which does create a vector field. At every point x, y, it's going to create this vector, which is the partial derivative with respect to f, or the partial derivative of f with respect to x, the partial derivative of f with respect to y at every point, but it's creating a vector. So that is what we're going to call the gradient vector field of a function of two variables. And exactly the same, if we have a function of three variables, that still creates a scalar, but from this scalar valued function, we can create a vector field called the gradient vector field, which is of course going to be completely analogous to the two-dimensional case, where we have a gradient vector field of a function of three variables using the partial derivatives. And again, they say this a lot, but what does that field do for us now? It creates arrows or vectors at every point which are in the direction of the fastest rate of change for that function, which is extremely useful. A whole field which tells you the fastest direction at every point. Let's do an example. Okay, our last example of gradient vectors over R3. Again, now we're really going to want to talk about vector fields in 3 space because that's where physics actually happens, in 3 space and time. In every point in space, we've got a temperature, which is given by t of x, y, z is 100 minus x squared minus y squared minus z squared. It wants us to find the gradient vector field of this function, which shouldn't be too hard to calculate. Let's just remind ourselves. The gradient vector field of t at a point x, y, z is equal to the partial of t with respect to x, the partial of t with respect to y, the partial of t with respect to z. And that won't be hard to calculate. That gives me specifically negative 2x, negative 2y, negative 2z, which is by scalar multiplication of vectors in 3 space, negative 2 times x, y, z, which wasn't necessary. But the interpretation of this is the maximum rate of change for this temperature function at every point. Next time what we're going to do is we'll do more vector fields, and we'll talk about conservative vector fields and non-conservative vector fields. And then a major question in the rest of this course is going to be asking ourselves, when are vector fields conservative and why did we call them conservative? Please subscribe right here, hit the notification bell. I'll see you next time.